Now we are going to show you a demonstration for using the spreadsheet to solve for the optimal design of water supply system for the Thurstville problem. In most of my spreadsheet models, I like to use divide the sheet into sections. One of them for input data, where I expressed every variable in terms of 4 columns, one for symbol, one for value, one for units, and one for definition. To calculate the rest of the design variables, I have to add a section for the demand curve, where I summarize the demand curve into 2 columns, one for duration in hours and the other for flow in cubic meters per second. Then I have another section for design calculations, where I calculate HF, horsepower, average flow, and volume of reservoir. And every function of this, the formula appears in the formula bar here. Therefore, this shows you the details of how I calculated HF, and here how I calculated HP, where variables, as you know, refer to cell address. The same thing goes for Q average, where I use the sum product function and I divide 15 by 0.2 plus 9 by 0.6, divide the whole result by 24 hours. The same thing goes for the volume of the reservoir. Then I add a section on cost calculation. And here I calculated the cost of the pipe from the cost pipe formula. The same thing goes for the cost of the reservoir and the cost of the pump. Then I add the 3 cost values to get the total. Therefore, if I use a diameter of 0.5 meter and a discharge of 0.5 cubic meters per second, I get a total cost of 1,017 multiplied by 1,000 in dollars. But this is not the optimal solution. The optimal solution can be obtained by using the solver. I use data and then I use solver. And here I point to the total, which is the target cell or the set objective, and it's a minimization problem, and I have to use to point out to the variables, which is the D and Q. Here I put an upper limit on the discharge and a lower limit on the discharge, and I add also 2 other discharges for a reason that I will tell you very soon, for diameter. Therefore, for diameter, it has to be less than 0.55. These are available diameters. And I add to this the same thing D, but here it will be greater than or equal 0.35. Then by doing that, I will change the optimization procedure and use evolutionary. And this is why I added limits for diameters, because for evolutionary methods, you have to put limits for all design variables. Hopefully, if I push solve, I get the optimal solution. Let us see what happened. A5. Okay. This is supposed to be B5, not A5. Okay, and then I will solve. It may take some time, I don't know why. Yes. It has a solution here, and it has an optimal value. Therefore, I will keep the solver solution, because this is the same value we obtained from before when we talked about the solution, the hand solution and the cost surface before. But Excel can also find a solution if I have discrete values for both diameter and discharge using what we call a two-dimensional table. And we solve by enumeration. I am going to show you how we can do that. See here. This is the optimization by enumeration. How do we arrange this? We put all possible discrete values of pipe diameter in a row here. And this is why I put the limits for the diameter in the previous optimal solution between 0.35 and 0.55. And these are the flow values incremented by 0.05 cubic meters per second. This particular cell refers to the total cost for the model that we calculated before. Because we kept the optimal solution, it has here this solution here, which is the same as 1,009 multiplied by y side $1,000. But what we want to do, we like to repeat this calculation as many times as the numbers of candidate diameters multiplied by the numbers of candidate flows, and the solution will appear here. But in order to do that, we have to highlight the whole table like this and go into data. This time, we don't use solver, we use what if analysis, and we use data table. When we use data table, it asks me, where is the row input cell, which is the diameter? Therefore, I will go and click for diameter. And the input column cell, I will mention discharge. Then I will click. Then after I click, I get all possible solutions, the total cost due to combinations of discharge and diameter. After that, I can use a simple function to calculate the minimum cost. And then out of this table, I'm using the minimum, and then I highlighted this range and discovered that this is the minimum discharge, the minimum cost, and the optimal values of diameters are 0.4 and the optimal value of discharge is 0.35 cubic meters per second. By this, we solved the same problem 3 times. One of them using an assumption of D and Q, and then we used the nonlinear problem solved by a very specific way of solving optimization methods, which is evolutionary. And in order to do that, we have to put limits on both variables, D and Q, and we obtained an optimal solution that we obtained before. And the third solution is done by enumeration, where we use the two-dimensional table in the what-if analysis options to find the total cost for combinations of pipe diameter and flow.